inviting me to a fascinating conference, to Petra and David. And I always have a bit of trepidation coming to talk at metaphysics conferences because I'm pretty convinced that the stuff that I'm doing about chemistry is interesting from a metaphysical point of view. On the other hand, I don't really kind of develop it. That's not my business. I'm not a metaphysician. So I don't develop it in the kind of detailed way that you guys have been doing earlier on. So I'll make a few sort of gestures towards. Hopefully, it's not sort of egregiously mistaken about naming the view. So what I'm going to talk about basically is three parts to this talk. The first part, I'm just going to defend microstructural essentialism. I'm going to say why I'm going to defend it, and the second thing I'm going to do, which I think you have to do if you're going to be a microstructural essentialist about chemistry, you have to give an account of what structure is in chemistry. Interestingly, no one has really done that before, like philosophy. I mean, obviously chemists have been working on it all this time, but they don't use the term microstructure. They just talk about structures and things. But microstructure I take to be things happening at the molecular scale, which is about the nanometer scale. And then finally, I'm going to move on from that sort of view. If there are constraints on that view, that mean you have to accept things, and then you get some interesting results about how existence and composition work out, and in particular, the existence of composite objects, which basically is what chemistry deals with. That's what everything it deals with is composite. And there's, so hopefully that'll be interesting. So I'll start. It might not sound like a very interesting thing to do to defend microstructural essentialism, but I was led to it by two things really. Quite a few years ago, Ian Hacking wrote this article about the term natural kind and how he just that it had no place in philosophy of science anymore. It had been ruined by the metaphysicians and we should have given up and stopped using it. I just read the paper and thought, well, I kind of agree with you about a lot of a priori constraints being coming in and fitted onto something which the discussion of which had initially lacked those a priori constraints, but we should take the term back rather than giving up on it. So that's partly what I'm trying to do. And going back to the same source, really, John Stuart Mill, that Hacking identifies. The second thing is, I've always found it curious that there's a form of argument in the philosophy of science where someone says, Kripke-Putnam essentialism. Kripke-Putnam essentialism must fail because, look, here's a kind term which doesn't work that way. And so a really well-known example in the philosophy of science literature is a paper by Carl Stanford and Philip Kitcher where they talk about acidity. I think they're right about acidity, but I don't see how that's got any relevance to what you think about the chemical elements. So, and you can give a highfalutin name to accepting that essentialism might fail for acidity and might succeed for the elements, and I call it meta-classificatory pluralism. So it's just the thought that conceptions of natural kinds are explanations, possibly metaphysical explanations of the fact that something is used in science for making things like inductive inferences, and it's central to explanations. And there are different kinds of, so essentialism is just one kind of explanation of why we can do that. For instance, to use the element names to make predictions about, use elemental composition to make predictions about the behavior of substances, which is what chemists in fact do. And just finding that, investigating whether that's a right stance to take on the elements, it's got nothing to do with whether it's a right stance to take on acidity, which actually turns out to be a really interesting story, but I'm not going to say anything more about it. I can tell you something about it if you'd like to hear about it. And And another example of this is Joseph Laporte's discussion of jade. I mean, you don't see, if you open a chemistry textbook, even chemistry textbooks, in an inorganic chemistry textbook, the term jade wouldn't appear. You might have jadeite or you might have nephrite. Chemists don't group those two. There's no reason to. So he's talking about something else. So there's the other sort of thing about that's a different kind term. If that's a natural kind, I don't think it is. Then it's a different kind of natural kind, and therefore has got. And there's quite a few recent papers in the literature which attack essentialism, and it is a bit of a target in the philosophy of science. People think that essentialists sort of going around making essentialist claims about everything. Well, obviously, I don't think you should be doing that. I think you should be investigating the scientific details of how things have gone in each particular case, and then you can look at particular kind terms or classes of kind terms like the elements. So I start out with try to kind of reform the discussion of natural kinds a bit by going back to the source and thinking, and kind of by stipulation, saying, well, I'm going to make a microessentialist claim about chemical substances. And chemical substances are stuffs viewed from the point of view of chemistry, which has got a particular way of looking at things. And what it expects is homogeneous and homogeneity, compositional homogeneity across particular samples. I like to link that up with Aristotle's famous claim that every part of water is water. Every part of a substance is homogeneous. Then, and also that there is same as composition across different samples. So this is a nod to my friend Paul Needham. Thermodynamic criteria are relevant to, but not constitutive of, being a chemical substance. So, for instance, thermodynamic behaviour, like boiling points and things, I hold can, if you understand chemical substance names the way the chemists do, can vary across different possible worlds. So there's examples: oxygen, gold, water, ethane, and benzene. I'll come back to some of those. But then there's other kinds of stuff, there's other kinds of stuff. There's no assumption that particular samples are going to be homogeneous from a chemical point of view. So if you take milk, for instance, milk is something that is produced by mammals for nourishing their young. It will vary across different mammalian species. It will vary across the particular lifetime of an individual and the milk that they produce, depending on their diet and other physical conditions and so on. So we just don't expect wool. There's another one. Different sheep are going to produce different kinds of wool. Silk. There's just no expectation. So with the chemical substances, chemists kind of decide on what the extension of the term is at that pattern. But on the other kinds of stuff, there's other people who do that. So or maybe it's biologists who are going to decide what counts as milk and when, and how far you can get away from the central case, as we think, and so on. So it works both ways. So you could, if you take silk, for instance, you could have, you can imagine an artificial silk which was atom for atom identical with some real silk, but the real silk was real silk because it came from a silkworm, and the artificial silk it didn't because it came from a chemical laboratory. So that's the important point there. So if chemists have got a role in analysing, which they of course do, the chemical composition of the other kinds of stuff, it's a kind of a service role. They come in after the extension's been fixed. You can say, well, this particular sample of milk has got this in it, or we can make generalisations about milk and so on. It just seems to me the obvious move you have to make, and it just like renders all the points that Laporte makes and other people who make these pluralist points entirely irrelevant from the point of view. Just because there are other substance names, they're just not chemical substances. They're something different, and they work differently. So they might, one still might want to say they've got essences. There's something that makes them milk or whatever, but that's not something I'm going to take a view on because I'm making a claim about chemical substances. So this is the point about going back to Mill. A natural kind is one about which science can make reliable inductive inferences. So we just start from that base, and then we say, well, there's different kinds of explanation of something being a natural kind, i.e. the ability for scientists to make reliable inductive inferences about it. Yeah, I've been challenged to extend that to include explanatory inferences as well, but I'm not entirely sure that's. Yeah, but we'll just stick with the source at the moment. That's Mill, and he was clear it was inductive inferences. So essentialism, then, we can see as a particular kind of explanation of the fact that some particular science can make reliable inductive inferences about some particular kind, appealing to properties that are necessary and sufficient for kind membership. That's the key point. And then metaclassificatory pluralism, defending microstructural essentialism about one kind or one group of kinds is quite independent, depending about another. So just don't take on that work. It's just a confusion. And realism, just the thought, the claim that some particular kind can be known independently of knowing what that kind is. That's always something my late colleague Jonathan Lowe used to deny if you didn't grasp what it was. Yeah. If someone can produce something, yeah, it's. So, defending microstructuralism. So here's three immanent arguments. I.e. arguments that they're based in chemistry, that's what I mean by them being immanent. Chemistry uses microstructural properties and relations as the basis for a systematic nomenclature, and it's been doing this progressively since about 1790 when Lavoisier identified composition as a way of naming compounds. It's the binomial nomenclature that we, carbon dioxide, that binomial nomenclature is something we basically inherited from Lavoisier. You can take the IUPAC is the International Union of Pure and Applied Chemistry. There are people, they write a book on, there is a name for every chemical substance based on its microstructure. So this here, this is TNT, which is actually an old-fashioned name for it, trinitrotoluene. It's now called 2,4,6-trimethylbenzene. So it's called that because that is benzene, that is methylbenzene, or toluene in the old terminology, and then here's three nitrate groups, and they're numbered 2, 4, and 6 as you count around the ring from the one that defines toluene. So trinitrotoluene, it's just like lifted straight out of the microstructure. So there's one thing. So the chemists have decided, and you think if anyone knows, they should know, the chemists have decided that this is the right way to give systematic names for things. Secondly, microstructural properties and relations, that is, relations, we'll get into what they are central to explaining chemical and physical properties. So the course of reactions, how they go, the detailed mechanisms, the step-by-step things that happen, transfer of electrons and so on, and their interactions with radiation. There is no other game in town in terms of explaining what's going on. There's no other basis for explanation. And then finally, I put Tina in there. That apparently that used to be a nickname for Margaret Thatcher. There is no alternative. Tina, there is no alternative. So I've got some other paper. You might think you could come with an alternative way using classical thermodynamics. That's one of my friends, old friend Paul Needham, who tried to show how to do. I think that fails. I've got a 2010 paper in philosophy of science I'm very proud of, but nobody ever reads or cites, all about how the entropic criterion for distinguishing substances, individuating substances, fails. It can only work if it draws on microstructural information. That's why. Otherwise, it comes up with something which is different from chemists' classifications. So, replies to three objections. Some substances are heterogeneous at the molecular scale. Water. So what water molecules get together, we'll talk about this a bit later on. We've got a model for it. Water self-ionizes. Not very much, about 1 in 10 million molecules does this, but it's enough to be the key reason why water has got anomalously good transport properties, which is why you can't take electrical things into the bathroom. It's a very interesting process, actually. So, and the heterogeneity at the molecular scale of water, the fact that it's made out of not just H2O molecules, but all sorts of other species as well, including sometimes long strands of water molecules linked up to each other and transfer charge right across quite a large body of water, that's a reason for taking it as a property of water, I think. Then the right way to think of the microstructure of water is that molecular population which is produced when you bring H2O molecules together. That's what you've done. You can take some widely separated H2O molecules, bring them together, they'll start interacting. So they're not interacting very much. They get together, they interact, and they do this thing. They could do it differently in other possible worlds, maybe. In fact, chemists seem to think about things in that sort of way. So we've got to think of water's relationship to H2O as being a productive relationship. So water is what you get when H2O molecules get together and interact. They produce this thing. Secondly, there are some stuffs or types of stuff which microstructuralist essentialism can't account. So as I've already said, that's not relevant. What's required is a chemical substance for which microstructuralist essentialism can't account, and people actually don't produce those. They produce things of other kinds of stuff. The third kind of objection one sees, I had this, I sent a paper on instant days one time, and the referee's comment came back that this person should read Robin Hendry's work because he didn't think it was rubbish. He'd be disabused of this nonsense this paper's arguing for. I mean, it's reductionist. Well, I don't think microstructurism is not reductionist, so that's my answer. Oh no, it isn't, because it is perfectly compatible. Well, it requires only, or it establishes only a weak dependence relation, and that's kind of physical exhaustion between substances. But as I've argued in various places, it's perfectly compatible with a strong emergentist view of substances in their relationship to their microstructural components. So, from microstructuralism to, so I don't think regard any of that as, that's just microstructuralism. That just tells you what the chemical substances are and how they're individuated. Doesn't give you microstructuralist essentialism. Two classic roots. I mean, I think everybody says, oh, the semantic root, the quick recovery style route, where everybody's using the term water. Chemists look within samples within that extension, and they find out what's in there, and then they've identified what it is to be H2O. There's lots of reasons to be. One thing is that the idea that there are the relevant kind of linguistic regularities right across languages. That's clear. That's very suspicious. However, all that semantic root stuff, thinking that the Cooklian Putnam did in philosophy of science, it's really useful for doing semantic things like establishing continuity of reference across major conceptual changes in science. Very useful for that. That's a semantic task. Great for that. No help with identifying, making a metaphysical point about. Another possible route is scientific essentialism. Brian Ellis's who set up basically a priori considerations. He in fact used chemical kinds as many of his central examples. Unfortunately, they don't satisfy the a priori constraints that set up. That's hierarchy, discreteness, and interest independence. Independence from interest. I don't think that it satisfies any of them. They satisfy any of them. But that's a whole other paper. So that's not a route to go either. So the route is to take chemistry seriously in what it's saying, and realise what it's telling you is that the only way to bring into being a sample of a chemical substance like water is to bring into being an instance of its microstructure, so whatever its microstructure is. So then we can say, well, after chemistry, the structure of a substance, the molecular scale is its very being, whereby it is what it is, how it presents to us, and so also how it does what it does, how it interacts with other substances and with radiation. So that was microstructural essentialism. But then there is still a question: what kind of a thing? And it's a bit depressing, whatever it is. This microstructure is whatever it is you get at the molecular scale. That's underlying, that's using to. But why is that? So, what is a microstructure? Can we say anything in general about what a microstructure is? Well, there are two desiderata to apply. One of them, that in particular a theory of structural chemistry comes into being for a particular reason, and that's to explain isomerism. It comes into being, certainly in the historical sense, in the 1860s. That's why theories of structure. Because after Lavoisier, chemists got into the business of analysing the elemental composition of substances, and then they realised that there were substances that had the same elemental composition. Those are isomers. So if you've got the same elements in the same proportions gathered into a substance, then they must differ in the way in which those elements are combined. And that's the way, that's what I think the structure is. So I'll give you an example. Here's Here's ethanol, the active ingredients in whiskey, and here's here's dimethyl ether. I did once have a philosopher say to me, why can't we just regard them as the same substance? Well, because that's poisonous. Well, that's poisonous too, but over a longer time scale. This one boils at minus 24 degrees, this one boils at 80 degrees. They're different stuffs. So, the thing, all we've done is taken the oxygen atom there, we moved it in between the carbons. That's all that's going on. So, these formulae, these structural formulae, are an explanation of how it's possible for there to be two substances with the same chemical, with the same elemental composition, so the same elements in the same proportions, but they're actually totally different. They must be combined together in different ways. That's one way, that's the other. And that's basically what a theory of structure has got to give you, primarily. Later on, that's from the 1860s, later on the theory got more ambitious and started to explain, it was developed quite extensively to explain the interaction of molecules with radiation and stuff, and the course of chemical reactions in detail. So there's one desideration. The second one is that matter is always in motion, and nomically that's non-accidental. Quantum mechanics tells you that there are detectable zero-point motions for anything at the molecular scale. So there's always a minimal amount of motion. You can't take all the motion out of a quantum system. So they're always going to be wiggling about. It's called a zero-point energy. Zero-point motions. So they can't be got rid of. So what that tells you is you've really got to take into account the fact that everything's moving down there. So here's an example. Let's take ethane. So ethane was what I was about to draw. Ethane is slightly different. It doesn't have any oxygen in it. Ethane is C2H6. There it's simply... now I take that molecule and look at it end on. The hydrogen atoms aren't in fact at right angles to each other. They're kind of they're like that. So the carbon atom is tetrahedral. So so if you look at them end on, you see this. Those two the big round things are the two hydrogen atoms looked on end on. So we're looking at molecule end on. So these things are described by Bassendale, a marvellous book called The Third Dimension in Chemistry. It's a lovely little book. He says, ethane can be thought of in terms of two linked CH3 propellers with each CH3 rotating rapidly. Now, really rapidly, like millions of times a second. So they're bumping around. So you can distinguish that stage where the hydrogens are offset from each other, and that stage where they're eclipsed. They're shown slightly offset here, but you can imagine them. Now that, because the hydrogens interfere with each other, is a slightly higher energy situation. So these propellers, they're going round, but these, because the eclipsed conformation is slightly higher energy, it's kind of bumping, like going over lots and lots of little speed bumps in energetic terms. So that's called a Newman, and that's called a Sawhorse projection. So what does that tell you? It tells you that in ethane, its structure is basically represented by that, and not necessarily its geometrical structure, which is the geometrical structure is changing all the time. So the spatial relations that the atoms have with respect to each other. Another example is cyclohexane, which is just like a six-membered ring with lots of hydrogens, and it flips 1,000,000 times a second between different these things called conformations, which are basically the geometrical things. Between different chair, that's called chair, that's called boat, you can probably see why. Exhibiting different geometrical relationships between the constituent atoms. The bond structure, though, is constant throughout, as it was in the case of ethane, and it's the bond structure which really constrains what the available conformations are. And so you can think of the bond structure as being obtained, although the bond structure was historically prior, the bond structure is kind of explanatorily prior to the geometrical structure. That's my view, because it's the thing that's constraining the relative energies and so on of the thing. It's those bond linkages which are constrained on the molecule, the motions of the molecules. And then there's water. I said I'd say something about that. So Paul Needham challenges and said, well, what is water's microstructure? In his, this is a lovely short paper in analysis from about 20 years ago, and he says, well, it's actually really complex. Putnam says it's this, but it's not that. It's really complex. So there's two things going on. One is self-ionization, and secondly, there's this process of forming hydrogen-bonded linkages between the water molecules. And that really structures what's going on in the liquid. So you can look at these things as like big molecular, oligomolecular structures. So they're made of a few molecules. So really all you can say is that, this is why I say that water is what you get. The water that we see is what you get when water molecules interact under the laws of nature, the actual laws of nature. So, and it could be different. Sometimes chemists reason this way. So chemists often say that water's boiling point is enormously high because of all this hydrogen bonding here. So the water molecules have got extra strong attractions for each other based on partial charges on the oxygen and hydrogen atoms. And they say that because otherwise, if you look at water in comparison to other hydrides in its group, then there's kind of a linear relationship with the molecular mass. So I got a paper on this in analysis a few years ago. And then water, it just like makes a linear relationship and then boom, water's up here, it's looking anomalous. And then what chemists say is that, well, it's what makes the difference from what you would get if water was like the other compounds in its group, if it was what you would expect. The difference is hydrogen bonding. That's the difference maker. So what I understand that to mean is they say, they identify what water's boiling point would be if you switched off the hydrogen bonding. So I understand that to mean that water's hydrogen bonding is, they regard as metaphysically contingent. So it's something that's, it makes sense to talk about something being in water without having hydrogen bonding. Okay, and the take home from all this is that structure is abstraction. We've got different kinds of structure. We've got bond and geometrical structure. There's a scale relativity of geometrical structure, which I haven't really talked about. Secondly, as I've pointed out, molecules are always in motion. It makes sense to see them as processes. I don't think that it's not to introduce process ontology. I think that we should just move between process and substance ontologies. Molecular species interact in quite different ways under different physical conditions. So if you want to talk about the structure of something, then you have to look at all the properties and relations that it has across various regions of time. I should say time scales there, or energy scales. So, and this isn't to reject realism, because abstraction here is partial consideration. We're not going to abstract objects or anything else like that. We're just concentrating on certain things and leaving out others that vary across samples. So, for instance, if you want to take a look at, think about ice and liquid water and steam, then what they've all got in common is that they are molecular populations or structures that are being produced by the interaction between H2O molecules. That's what they've got in common. So that's what tells you that water is characteristic of those different phases or different states of aggregation. And so we're just attending to the, as it were, to the molecular composition and abstracting away from the different ways that the H2O molecules are interacting, in each case, the different structures that arise from that at different temperatures. Now, finally, I get to existence and composition. So maybe I could have said a bit more about scale relativity of structure. Two things, basically. I'll just skip over that because it's time's going on. I'll move on to existence and composition. So I've said that structures are scale relative. I've said that also what substance something is determined by its microstructure. So because the way those things pan out in the actual physical world, there's some interesting results come up. And that's scale dependence or structural distinctness. So I don't know if anybody's heard this. For undergraduate chemists, it's a classic thing to look at. Louis Pasteur's resolution of racemic acid, which is sodium ammonium tartrate. Basically, what he did was he evaporated. He took a solution, a racemic solution of sodium ammonium tartrate, and he evaporated it, and it got left with some crystals. And he then went with an eye. He noticed that the crystals, and this had been noticed before, that some were kind of left-handed crystals and some were right-handed crystals. So he took the left-handed crystals and put them in one jar, and took the right-handed crystals and put them in another jar. And then he found that, so just crystals like this, one will be literally a mirror image of the other one. I think this is one of his diagrams. And I always think this is a bit like the Babel fish. I remember the Babel fish in The Hitchhiker's Guide to the Galaxy. It's something a bit spooky. Well, if you do this, if you dissolve that in water, or if you shine plain polarized light like that through one and through the other, This one will rotate plane. So plane polarized light, normally light is circularly polarized. So if you put it through a diffraction grating, you get what's called plane polarized light. So it's the the oscillations that make it light are all in one plane rather than being distributed randomly around in the direction of propagation. So if you shine plane polarized light through that, the plane of polarization will be rotated to a characteristic degree. You shine it through that one, it will be rotated to the same degree in the opposite direction, which is kind of spooky. When it was, and what Pasteur did was he showed that this must be a phenomenon at the level of how whatever it was that makes something sodium ammonium tartrate collects together in the thing. So it's something below the crystal level, because you can dissolve the crystal in water and you still get the same behaviour. So it's called optical activity. So anyway, so that's the backstory. The amazing thing is that he did this in Paris during the winter, and if he'd done it in the south of France, or presumably in the summer in Paris, he wouldn't have been able to do this, because above 26 degrees, the very same substance doesn't crystallise out to two separate left-handed and right-handed crystals. But the molecules, basically it's because you've got left and right-handed molecules. The molecules get together in one racemic crystal. So you've got what were two distinct possibilities, two distinct structural possibilities. You go above a certain temperature, and there's only one possibility. So if you tried doing that in Marseille, you wouldn't have managed. Here's another example, which is structural distinctness. So I hope these, maybe I'll explain the molecular structures a bit. These are benzene rings. They're flat hexagons. Basically, you've got one flat hexagon attached to another one by a single bond. Now, normally, a structure can rotate around a single bond. That's what we had, when you had the two propellers, there was a rotation around that single bond. You can't rotate around double bonds, which gives rise to, it's a constraint on molecular motion, which gives rise to a form of structural isomerism. Here, there's another interesting one. So, if you substitute these benzene rings, they're called biphenyls, so they're substituted biphenyls with some species, X and Y. And if they're bulky ones, then these, so if you see this one's flat and this one's in the plane of the board, and this one kind of tries to flip around. If that and that are bulky, they'll bang into each other. But of course, if you heat the stuff up, it will bang past it. So it's just like going over the bump in the road. But if it doesn't have enough energy, it won't get past it. So that interaction there will be a constraint on the motion below a certain temperature. So if you take any particular thing, substitutions there, you will find a temperature above which they can't be resolved, and at a temperature below which they can be resolved. So below that temperature, there's basically two separate structures, two separable compounds, and above that, which are isomers of each other, and above that, they are different. They bear a relationship. These are, if you can see into, these are actually mirror images of each other when they're constrained in that way. They can be. But the interesting thing is that the isomerism disappears above a certain temperature, because so that's what I mean by the scale dependence of structural distinctness. You put enough energy into the system, those structural features just disappear, the differences disappear. You've got two things. This is why I think it was crazy for Brian Ellis to stipulate that natural kinds in chemistry have got to be discrete. Natural kinds have got to be discrete, and then to take chemistry as the example. So here's an example where you literally can turn, by a continuous change, just turning up the temperature, you can turn two possibilities into one possibility. Okay. So that's one point. Chemistry has traditionally been very interested in compositional relationships. Composition in the sense of, well, it's always been interested in composition, like what things are made of. And there's a question of whether that's a pun with, for instance, use of composition in the phrase, Van Imhoven's phrase, the special composition question. I don't think it is. So chemistry's always been interested in compositional relationships between substances. Aristotle was. He said, when is it in that composition, when do two things make a new substance, and when do they? He thought the atomists couldn't explain why, how it's possible for two substances to come together and if they retain their identity in the compound or mixed. So between substances, we've got the elements hydrogen and oxygen, and obviously they're components of water. Then there are compositional relationships between substances and species at the molecular scale, and then there are compositional relationships between species at the molecular scale. So there's things like when electrons and nuclei are actually the components of molecules rather than atoms. And it's this one that really that I'm interested in, because chemists are interested in it, and it maps very nicely onto the special composition question. I could say a few things about the whole setup of the special composition question. I mean, it's a bit of a pseudo question in that I don't know how many people will disagree with this here, but whether the idea that nihilism gets a free pass because they've got this form of words that says symbols arranged chairwise or so on, or atoms arranged molecule-wise. Until you know what, and the claim is that this has the same as a pragmatic content as the actual explanatory use of the composed objects, but we don't know what an arrangement is. It kind of seems plausible because there's this idea of an arrangement that's, that's an arrangement, that's another arrangement, but that's not what's going on in structures in chemistry. We've seen that. That's far too thin a sense of the kind of relationships that the components of things bear to each other. So that's why I say nihilism isn't in fact a position in the mereology debate. It's a form of words that lots of philosophers have agreed is a position, but it's not. It's not even worth considering because we just don't know what it is. Because we just don't know whether the nihilist position is able, with a form of words, to come up with something which is, as it were, pragmatically equivalent to genuine explanatory appeal to composite objects. Until we know what arrangements are, we just don't know. Oh, right, got that off my chest. Now, Kerry Mackenzie and Fred Muller, a few years ago, came up with a nice little paper in giving how Van Imhoven, the nihilist positions, the universalist positions, and the moderate position. They come up with a moderate position on composition. When do the x's compose a y? So that's nihilism, always universalism, and sometimes that's the moderate position, and you've got to keep the conditions. So they come up with a condition in their philosophers of physics. They give a physics condition, and that is that physical objects form a composite object if and only if those physical objects interact and are bound in a common bound state, and are in a common bound state, where common bound state means that the composing objects are in the potential well that results from their mutual physical interaction. So the idea is basically this. If you take two hydrogen atoms and sort of bring them together, then there'll be a number of interactions. So remember, I had two hydrogen atoms, that's two protons and two electrons. It's very simple. It's the grade one, properly molecular system that counts. So there's going to be some repulsions between the like charges, there's going to be some attractions between the opposite charges. There's a whole bunch of other quantum mechanical stuff going on called things like exchange forces and so on. All that sums up if you into something like this. So if you this is a graph, that's energy, and this is the distance between the hydrogen nuclei. Obviously, if you push the hydrogen nuclei too close together, they'll really start repelling each other, so the energy goes arbitrarily high. You pull them apart, they become indistinguishable from two separate hydrogen atoms, and that's what this level is. So this is the potential well. So they're kind of, the idea is that they're caught in there. So that works fine in that case. I don't think it works well to other cases. There's a couple of things going on. First of all, they don't say what a potential well is a minimum in a potential energy surface. So if you have a map of energy as a function of the configuration somehow, the structure of the thing, they don't say whether it's got to be a global or a local one. And as we saw, remember how we saw, molecules always in motion, and they've got little constraints on their motions. They've got little hills they've got to bump over, like the rotating ends of the ethane molecules. So there's three little potential wells around there. Those don't form constants. One wishes to say those don't form sort of separate existences, because that's just a single existence, so an ethane molecule doing what it does, which is rotating. Secondly, there's the issue of timescales, and I think it's interesting. And if you focus on timescales, there's a nice little puzzle you can solve. And there's an Aristotelian sort of take one you can make on this. So I'll get on to my last slide. So here's the three cases. Hydrogen and helium dimers. Dimers are just, you've got two atoms of the same species, and you make what's called a diatomic molecular atom. But there's transition states and reactive intermediates, that's these things. And then there's super heavy elements. So Ludwig Yankton was talking about those earlier on when he talked about the transuranic elements and how some people regard them as different from the elements at the beginning of the periodic table. My focus on timescales gives you a lovely explanation of why that's justified. Anyway, so hydrogen and helium dimers. Things are a bit more complicated because, as I say, there's little potential energy wells all over the place. The interactions of atoms give rise to energetic changes which produce little energy wells all over the place. Second year quantum mechanics course that chemists are taught, you'll always, first thing you do is you're taught, well, here's hydrogen exists because when you bring hydrogen atoms together, the two hydrogen atoms is a hydrogen molecule. This here is the kind of average distance between the two atoms, the two hydrogen nuclei. Is of lower energy than the separate thing. So once the hydrogen molecule is trapped in there, unless something comes to kind of dig it out to give it out enough energy, they're kind of bound together. So they've got to move around as a single thing. There can be vibrations, so they'll typically be doing this. In fact, we know there'll be double vibrations because there's a 0 point energy for the vibration, so you can't remove the vibration energy. So, but there's a snapback. There's something pulling them back, and that's the overall effect of the interactions between those two electrons and those two nuclei. So there's a pullback, and that's why we can interact with this. Those vibrations explain how an individual hydrogen molecule interacts with radiation. So interacts with radiation, it absorbs some energy, and those vibrations, movement between those vibrational states that explains the spectroscopic behaviour of hydrogen. So I'm saying that because this is how we explain the characteristic powers and susceptibilities of hydrogen, the substance of hydrogen, the molecular substance, on the basis of its microstructure. Contrast that with helium. Now, Helium. So we'll talk all of that in the quantum chemistry 201. It's not a first year course, it's always a second year by the time we get to that. Helium's different. When you do the same calculations, it turns out that the helium, there's basically nothing holding the helium together, so they can just drift apart. Now that's not quite true, because there's some things called van der Waals forces. So remember that helium atoms are, for anyone who knows, they've got 2 electrons. There's a helium nucleus, it's the same as an alpha particle if you've heard of alpha radiation. Helium nuclei, they've got a charge distribution. Left to itself, it's spherical, but there'll be kind of random fluctuations which make it asymmetrical. So if you've got a whole bunch of helium atoms floating around separately, and some of them just go, and they just flip over into an asymmetrical state, that will induce an asymmetrical state on the basis of its neighbours, all its neighbours around it, and then they'll affect their neighbours. So you get these forces, very weak attractive forces between the hydrogen, between the helium atoms. So it's not quite true that there's nothing attracting them. There's no chemical combination that's holding them together. So at room temperature, if you have 2 helium atoms kind of approach each other, they will form what's called a van der Waals dimer instantaneously, but they'll just bounce off each other because they're flying around with so much thermal energy that the tiny little potential well that there is just can't hold them. And that's why it's not enough for Mackenzie and Muller to say they're in the potential well, because you need to know how long they are and whether there's anything pulling them back into that potential well, and you need to know how deep that is in relation to the the energy in the environment. If you go down to absolute zero, very close to absolute zero, those van der Waals forces become significant, and you get significant amounts of formation of dimers and other species between hydrogen atoms. And that's detectable with all sorts of crazy quantum stuff that then happens, Bose-Einstein condensation. So you can detect the formation of under the very same forces at absolute zero, but you go up to room temperature, nothing's going on. There's just a collision, so nothing's being held. So that's why I don't think Mackenzie and Muller can be right, because it's not enough to be in a potential well. You've got to be in a potential well for long enough, and for the things to kind of hang together and to be held together. So the overall energetic situation in relation to its environment. So they're basically kind of bumping over just the same way that the ethane propellers are bumping past each other. They're not forming distinct structures, they're just kind of moving. And you get a similar thing with transition state of reactive intermediates. So if you, when you want to analyse reaction mechanisms in chemistry, you might start with the reactants over here, the product over here. Here we've got what's called an exothermic reaction, so the reactants have got more energy than the product, so energy is given off, exothermic. But sometimes, typically there's what's called a kinetic barrier to the reaction happening. So you've got to put some energy in order to make this reaction happen. Not always. But then sometimes there's a little slightly more stable structure here, and that's what's called a reactive intermediate. So it's kind of something intermediate between the reactants and the products. This comes from a really famous book on, 1950s book on, it's either called Mechanisms and Reaction in Organic Chemistry or Reaction and Mechanisms in Organic Chemistry. There's 2 books with those titles, some really famous books. Anyway, but this one, and it's a very nice thing. It distinguishes between the cases A and B. A, this thing is going to move over there, it's going to bump over that little dip, and you'll just proceed to the products. You won't be able to isolate something in A, but if B is deep enough, and it's just like a continuous change, you can just make slight structural changes to go from A to B. Sometimes you can separate out the reactive intermediate. You can identify it spectroscopically. Because remember, if it's down there, then there are going to be, there's a geometry between the atoms, and they're going to be vibrating. So if you've got some way to access the powers and susceptibilities, it's going to live long enough for you to detect it, i.e. for it to exercise its powers and susceptibilities. So it's kind of down there living long enough. I mean, but if it doesn't live long enough, even to go through a single cycle of its vibration, then of course it can't exercise any powers and susceptibilities that are associated with that vibration. There is a punchline to this. I will get to a thing. So there's two ways of looking at this. One way, kind of a pragmatic way that some philosophers of science like, well, it's detectable, some chemists take. Well, it's detectable. If we can detect it, then we can say that it's real. But that's not very, that's unsatisfyingly non-ontological. So you could say, well, the detectability relies on the species there exercising its characteristic powers and susceptibilities, which are characteristic of the kind of structure it is, and whose explanation of the possession of those powers and susceptibilities is directly related to the structure. So there's the argument, and that's the difference between what's called the stable intermediate and what's called the metastable intermediate. Then it's quite funny what's called metastable. I don't know if you know that diamonds, there's a famous song, "Diamonds Are Forever." Well, actually, from a thermodynamic point of view, diamonds are in a state of spontaneously transforming into graphite, because they're what's called a metastable state. So they spontaneously transform into graphite. It's just the spontaneous change is very, very slow. There's lots of changes like that. Glass, which is an amorphous solid, is understood in crystallography as trying to get into a crystalline state. It's just doing that very slowly, typically at timescales longer than the lifetime of the universe, but still, it's a metastable state. So I don't know how. That's the other thing about Mackenzian models. You've got some things which aren't in the lowest energy configuration, given all the ones that are available, but they're only very slowly changing, transforming into the lowest energy state. So can you say that glass doesn't exist or diamonds don't exist? And then finally, there's this example of super heavy elements. So in 2002, there was synthesized a new super heavy element. It's transuranic because it's past uranium, basically, but this one's way beyond uranium. Uranium's 92, and this one's 118. It's called oganesson. Now, I can't remember which group oganesson's in, but some chemists said, look, this isn't a proper chemical element. Now, one way of making that argument, which I would reject, which I've done in the paper, is that it's synthetic. Chemistry deals with synthetic stuff all the time. It makes things. That's especially started doing that in the 19th century. The other one, there's one element, technetium, which was named specifically for the fact that it was thought not to be naturally occurring. It was first isolated in the targets of particle accelerators. So when you're filing atomic fragments at other atomic fragments, you've got some technetium formed. So in kind of minute amounts, it was subsequently found to occur naturally, but there's no contradiction between it being an element properly and having. So there's various ways of it. Why can't it be a proper chemical element? Well, if you look at timescales, you can see why. Because oganesson has got a very, very fleeting existence. The timescale is in femtoseconds. So you put these things together, you basically bombard lots of one already very heavy atom with lots of heavy species, and they kind of very briefly glom together. They live long enough to get a characteristic signal from the nucleus. but remember that's like time scale of 10 femtoseconds, which is 10 to the minus 15. Now, to have chemistry, an atom needs to have a stable electronic structure. That's how chemistry works. You know, atoms, if you take a bare nucleus, but it could have a chemistry if you give it all the electrons. So if you go from, say, an alpha particle, you might think of a piece of radiation, if you give it 2 electrons, it becomes an helium atom, and therefore it's got a chemistry. It's kind of very uninteresting, dull chemistry, which doesn't interact very much with other things. Organeson, you can't do that, because organeson has already gone out of existence before, because if you try and take the electrons and put them around an atom, it doesn't happen instantaneously. It takes some time. So you have to put the electrons into around the atom, and then they've got to relax into their ground state. So that takes time. It takes about 100 million times longer than organeson exists. So organeson, there is presumably a theoretical electronic structure it could have, and therefore a chemistry based on that. But it can't have that, because under the laws of nature, the laws of physics, it's too unstable, it's fallen to pieces, it's turned into something else. So organeson, it can be a stable nucleus. So there's a good point. Should that appear on the periodic table of the chemical elements? Because if something can't have a chemistry, can it be a proper chemical element? All it is a physical. It's got, in some abstract theoretical sense, it's got the potentiality of doing that. But, so anyway, so I think that's a really nice way of using timescales. So you can have something can be, as it were, organeson the nucleus, but it can't be organeson the chemical element having a chemistry, because at the relevant time, it just can't live long enough to have the relevant powers and susceptibilities in this case of interacting with other atoms to form compounds and so on. Okay, I think that's it. Thanks very much.
We'll have a few minutes break. Now it's room till 5 minutes past.